Hi, this is Maxim Kuschnerov from Huawei, Germany, and I will talk to you about AI-aided DSP designs for coherent optical networks. Now, where do we stand with respect to how intelligent AI actually is? Are we getting closer to the final invention of a machine smart enough that it will continue innovating by itself without humans being needed? Or is it something artificial but not really intelligent? And if it is, can it be applied to a certain benefit in certain gain in today's AIs for optical DSPs? Well, let's look into this question. Well, researchers may ask themselves, why do we need AI anyway for coherent optical ASICs? In the last decade, we applied advanced demodulation schemes, nonlinear equalization, advanced error correction, constellation shaping, which bring us closer and closer to the Shannon limit. And Shannon limit is something which you cannot really surpass. So why AI then? Well, on one hand, the Shannon limit was defined for a very basic channel, whereas the fiber is a highly complex, nonlinear, multidimensional system. And if you don't think you need an AI in this kind of context, you just haven't asked a complex enough question yet. So where can we use AI for our DSP design? We can use it off-chip as to configure the ASIC, which doesn't contain any AI itself, by off-chip GPUs or TPUs. Example here would be a multi-dimensional nonlinear modulation scheme, which is optimized for a given optical link. Or we could even go to the next step and put deep learning and AI into the ODSP to act as part of the signal processing, as a nonlinear equalizer. Here, one needs to find a careful trade-off between the capabilities that complex deep learning has and actually implementability, making sure that it does fit into silicon. And if we look at the complete design flow of an ASIC, we see there's several stages, all requiring dedicated tools. And this EDA tooling can also be improved by using AI. For example, Google used AI to design chips that will accelerate AI. So it's a self-improving circle, although it's far away from the final invention. Now, if we look at what AI actually is in this context, I refer to the deep neural network as an example here. We see it has many neurons at the input, so it can accept many signals. And these so-called neurons connect to several hidden layers, or one really connects to everything else. So it's a highly complex network. Every neuron is nonlinear, in itself giving a highly complex, multidimensional way to map your problem and to solve such a given problem. So given the fact that this is so complex, why is it so useful? Well, I think in the first iteration, one doesn't really need to care about how to design it. We can put a generalized network first, and it can be adapted to various types of problems. It can actually adapt itself to it. Yeah? Whether to learn how to play chess, or learn how to equalize an optical signal. And in the second stage, of course, it would be interesting to go deeper after we have identified such a problem and optimize it for chip design. Now, mentioned before, the Shannon limit is maybe close, but it's not as close as you think. So why is that so? The optical channel consists of several high-speed components in the fiber itself, which all are, to a certain extent, limiting the capacity of the link. These components can be nonlinear. They can be bandwidth limiting. They can have noise, not just white noise, colored noise, quantization noise. They can have crosstalk. And this is a concatenation which makes it impossible to describe this link in an analytical form, meaning it's impossible to write down an equation from which we could derive the best way to compensate for this. This is where AI actually excels. We can look at the whole link as a black box which is stimulated by inputs, for example bits, and gets bits at the output. And what happens inside and how the network actually adapts to it, this can be really flexible. So the AI doesn't need to know about what's happening inside, but due to the sheer complexity and capability of this network, it can map many complex problems into a certain description. So which problems can we actually attack in modem design on a really high level? We can use AI for constellation shaping, probabilistic shaping, geometrical shaping, or a combination of these two applied to multi-band shaping and coding, which is really a multi-dimensional, very complex problem. Or one can use a deep neural network as a nonlinear equalizer and even combine it into one structure with a nonlinear demapping and soft information computation for error correction. So in a way, this network can map several different dedicated classical blocks into one, potentially extracting more information and giving the ability to improve the channel capacity. Now, one example for off-chip design. Here, examples of 800 gigabit per second, 1 terabit per second using classical modulation schemes measured over OSNR, using 32 QAM or 128 QAM. And we see that deep learning is capable of not only finding a better shaped constellation, which by the way is something that humans also figured out how to do without deep learning, but even more, it's possible to minimize the bit error, not just the symbol error. So these bit mappings here can be designed by the neural network really to not only have the best shape, but also the best bit mapping. And this dB that you get here is almost for free if the demapper is designed flexible enough to cope with different types of geometrical shaping. Now, if we take this training into the ASIC, look at the next example, we can achieve something different. In this case, we use AI as an advanced nonlinear equalizer. Here we compare a multi-band system with 800 gigabit per second, so it's an 800 ZR proof of concept transmission over 600 kilometers. And various equalizers are compared, all but one being classical, and this last one, green one, which achieves the best bit error rate, uses deep learning and combines actually several structures into one network. And as you see, it excels. It exceeds the performance which can be achieved by concatenation of classical algorithms. Now the problem with deep learning is that on one hand the demand for what we need to be computed is increasing so much faster than Moore's law is scaling. And if we want to keep up with this discrepancy, we would have to design, like this company does here, a very big, very powerful chip to cope with the deficiencies of Moore's law. As we see here, going from 10 to 7 to 5 nanometers, really, you get decreasing improvements on following up the node cadence. So what does it mean? Well, it means that if we compare the efficiency of such a 2 days implementation of AI to a human brain, although by itself it's not a fair comparison, because there's many applications where AI is definitely better than the human brain. But on the other hand, we all know that a small baby does better at distinguishing, let's say, dogs and cats and other animals than a chip actually does. Or who would trust AI these days with autonomous driving? Today, no one. So things which the human brain excels at only cost us around the power consumption of a light bulb, 20 watts. Whereas in this given context, a much dumber version of AI consumes 20 kilowatts for a server. Although this is still a very good number for this very advanced piece of engineering, which is a marvel in itself. So how do we break through to these limitations? Well, we need to look beyond classical CMOS. We need to look beyond von Neumann architectures where we separate CPU and memory. If we combine this into one block and remove the bottlenecks of memory to CPU interconnects, and at the same time go towards analog computing, which comes with the benefit of lower energy, but at the same time, of course, increases inherent errors because it's analog and has noise. If you can figure this out, we can actually break through a wall of post-Moore chip design and, for example, design large-scale neural networks where this multiply and accumulation function, the MAC function that we need for every neural network, can be efficiently designed by in-memory computing, drastically reducing power consumption. Coming back to the opening question of how complex does the problem need to be for us to benefit from AI? Well, if we take these modem design features where we already have seen that AI can give a benefit and combine this single modem view with a network optimization view and a planning for a complete mesh network, I think this is a problem which is complex enough to warrant the curiosity of research on AI. And I think this is also where AI really will excel and help us to design and configure and run and optimize these highly complex, multidimensional, nonlinear structures. So with this, I would like to thank you.